Okay, so let's talk about the Graph-Bert model, which is a new model proposed in 2020 actually by my group. So we try to incorporate the BERT and transformers for learning the embedding vector of the nodes in the graph inputs. In other words, we try to build a new graph neural nets by utilizing the transformer and BERT as encoders. So I hope you still remember what is a transformer, what is BERT, right? So the transformer is actually proposed in the paper. Attention is all you need. I mean, I assume you have read this paper already, right? We provide you with in the schedule spreadsheet. So in the transformer, we try to learn the input embeddings, but layer by layer, we only rely on the attention mechanism actually. I hope you still remember how we calculate the attention score among the inputs. I mean, for the transformer model, I mean, we use this QKV, this matrix, right, among each other, and we also rescale them by some term for controlling the variance, right? So this is a transformer model we plan to use, I mean, for the following part. At the same time, we also mentioned the BERT, right? The BERT full name denotes the bidirectional encoder representations from transformers. In other words, this BERT will try to use the transformer as an encoder for learning the embedding vectors for the text inputs. And they also incorporate some pre-training into the model architecture, right? And if we have a pre-trained BERT, then we can further transfer them or apply them into some downstream tasks with some fine-tuning. We didn't mention that with the transformer and BERT models, we can build very powerful models, and we also have different versions of a BERT proposed already, like GPT, right? So for the models right now based on transformers, they are very big. We also mentioned for GPT-2, now later we have 1.5 billion parameters to be learned. As to the GPT-3, we have 175 billion of parameters in state. When it comes to the GPT-4, for the new version of GPT to become maybe in next year or in the next year, it is estimated to have more than 20 trillion of parameters in state. It's very huge actually, right? So with the transformer and the BERT, we can build very powerful models for learning the embedding vectors for the text. And when it comes to the graph data, we can apply them as an encoder as well for learning the graph representations layer by layer. And you may wonder why we need to have a Graph-Bert, I mean, which is a new version of the GM models. The main reason is because the existing GM model may suffer from some problems, I mean, when we apply them to the real-world graph data sets. Besides the suspend animation problem and the overestimation problem we mentioned before, when we apply them with the deep architecture for graph datasets, we cannot learn the embedding vector anymore, right? Besides these two problems, we also have some other problems when we apply the GM model to the real-world datasets. The main reason is because the GM model they learn the embedding vectors for nodes with whole graph inputs. So because of this reason, I mean, when we apply the GM model to the real-world datasets, I mean the graph dataset, we may have some problems because the real-world graph dataset will be very big. If we apply the existing GM model to the small size of graph datasets, its performance is very good. However, when it comes to the real-world datasets of graphs with very large sizes, then the existing GM model cannot work very well anymore. And because of this reason, we propose a new version of the GM model, which is called Graph-Bert. So the Graph-Bert can address the above problems with some techniques or mechanisms inside the model architecture. So first of all, the Graph-Bert can address the suspend animation problem and the overstimulation problem with both the graph-related learning as well as attention mechanism in the model architecture building. So we can incorporate the graph-related learning terms we defined before into the Graph-Bert. At the same time, we also learn the attention among the nodes based on their self-inputs for aggregating their information together with each other. So to address the large-scale graph learning, in the Graph-Bert, we propose a new architecture based on the subgraph batching for learning the embedding vectors. And also we incorporate the Graph-Bert with unsupervised pre-training, and the model can be transferred to some other tasks via pipeline instead. And this model can be further fine-tuned for some downstream tasks as well for applications. So in this page, we show you with the overall architecture of the Graph-Bert model. This model will have 5 components: the part 1, part 2, part 3, part 4, and part 5 as shown here. So for the part 1, I'm given the graph input. We try to do some sampling of the subgraphs, I mean for each node in the graph dataset. For example, if we plan to learn a certain node representation, we try to sample a subgraph surrounding this node as a target node, as this one, right? And all the learning in the following part will be relying on the subgraph instead. This graph size will be much smaller than the original input graph, right? In other words, this Graph-Bert will be working based on subgraphs instead of the whole graph. If we have a very large scale input graph and like this one, then we will still be able to learn the embedding vector for all the nodes in the graph based on their subgraph instead, right? Also, for the graph, we sample from the whole graph inputs, and they have no edges actually. That's the reason why we name them as this linked subgraph batching, as we show here. So we sample one subgraph for all the nodes in the input graph dataset as for training. By fitting this kind of subgraph with no edges into the input for the second part, we can learn the raw embeddings. So the part 2 of the model attack is for learning the initial embedding vectors of the node's inputs in the subgraph. So given one subgraph, we have one target node. Describing the target node, we plan to learn inside embedding, from the graph dataset, right? Besides the target node, we also have a surrounding context describing what are the neighborhood or the learning contexts of the target node. So by fitting them into the second part, we can learn the embedding vectors for all the nodes in the graph. So it covers both the raw feature embeddings as well as embedding for the position information as well for all the nodes in the graph. The main reason is because we discard all the edges in the graph for learning the embedding vector for the subgraph, and we need to incorporate the position information of the nodes in the graph in the original graph by learning their position embedding vector as shown here. So for the part 2, we try to sum all the raw feature embeddings as well as position embeddings together as the inputs for the encoder defined in the part 3. So what is part 3? Part 3 try to utilize the graph transformer as an encoder for learning the embedding vectors for all the inputs as we show here. So this one is defined based on both the transformer as well as the GRES9 we defined before. We use all the initial embedding vectors for all the nodes as inputs, for learning the embedding vectors layer by layer. And based on this graph transformer, we can further fit them as input for the part 4, which is for the representation fusion actually. Because here we are trying to learn the embedding vector for the target node. And all the other nodes in the subgraph, they can provide some complementary information for learning the embedding vectors. That's the reason why we have one further fusion component here, and by aggregating all the information together for defining the target node embedding vectors. And this ZI vector will be learning the embedding vector for the target node as we're serving as the inputs. And this ZI can be further fitted as the input for the part 5 as shown here for some components for some application problems. And we define this part 5 as some functional components for applications. Now we can do either node classification, we can do the linear prediction, and we can also do the clustering as well. So this is the overall architecture for the Graph-Bert model we illustrate in this page. It will have 4 parts, and each of them will be responsible for different kinds of functions. The part 1 is for the subgraph sampling, and part 2 is for the initial embedding. Part 3 is for the encoder, right, for representation learning. Part 4 is for the fusion, and part 5 is for the application problems. We'll illustrate them one by one in the next pages for your in state.